this this homework. All right, so when I asked you guys to finish off number 2 here, I wasn't I wasn't expecting for it to be perfect. I just wanted you to attempt it. First thing that you need to do is just to sketch a graph of 2t minus 2, right? It's just this line right here, right? And we're letting a of x be equal to the integral from 0 to x of 2t minus 2. So a of x is the area function, right? That's going to calculate the area from 0 to whatever x value you want. And it's going to be the area that's between the function and the x-axis, right? So if I was, for example, if x was equal to 1, a of 1, right? A of 1 is going to equal to the area that is going to be from 0 to 1, which would be this area right here, right? And we talked about this. This area is underneath the x-axis, right? It's underneath the x-axis. That's why the answer for question part B right here, a of 1, it comes out to -1, right? Now, I'm not asking you to do this by drawing the picture out and then calculating this area right here, because if you go to x is equal to 2, when you go to this line, right, those two areas will cancel each other because one's negative, one positive. But on your notes, you're just supposed to use your graphing calculator to do this integral for you, right? All I'm asking you to do is just plug it into your calculator and evaluate these 6 points on here. Once you get those 6 points, you're then supposed to graph it, and then you're supposed to kind of see what that graph looks like, right? And when you graph that, it kind of forms like a U shape. And some students were able to figure that out in office hours, that U shape is just a parabola, right? And that parabola is something along the lines of, like, if you were to write the function for it, you would have hopefully guessed it's going to be somewhere along the lines of x squared, right? So this worksheet was supposed to make you build that connection to see that, oh, and when I graph the integral function, it graphs this parabola, but that just means that this integral function is the antiderivative of 2t minus 2, right? You'll say, but 2t, we had t's there, and this comes out as an x squared instead of t squared. And that leads us to this fundamental theorem of calculus part. We kind of call that variable in there a dummy variable. It's just a place variable for us right now, just to hold that spot for our x, which is technically right here. See that? It looks confusing when you have x and x like this. Well, your TI calculator can do that calculation for you. So when you graph this integral, you graph exactly what the parabola is when you were plotting these points, when you were evaluating these guys right here. So, I was bringing this up because whenever I get 3 people asking about the same thing, I get a little bit, I realize, like, okay, people are a little bit worried. Even though it's only 3 people asking this, that probably means there's more of you guys who are afraid to ask. So I just wanted to show that to you guys right there. Don't overstress this note homework. I just wanted you to see the connection between the integral and the antiderivative. Okay, that was the whole point of that. So when you come out to here, right, and they ask you, like, what is the value of a sub a, right? If it's going to go from a to a, that's just going to be 0. Okay. A maximum or minimum value of a of x occurs at a, right here, right? So f of t right here, right, occurs at a of x, a max or min occurs at a, I believe, what would that be called if the function at a, I hope you guys can see it, I believe it's going to happen at a 0, right? I'm thinking that right? Yeah, at a 0 of f of x. Meaning when the f function, or the original function that you're taking the integral of, right, if it crosses right here, you see that right there? It's crossing at 0. It's going from negative to positive. Look at the graph of a of x. The slope on this side is negative. It reaches this minimum, or this relative, this relative minimum right here at x equals to 1, which happens to be where f of t crosses from negative to positive, having negative slopes going to positive slopes. I'm quoting here because we're not actually looking at the slopes, but it relates to it. It actually has the negative slopes on this side, has a slope of 0, and then it has a positive slope on that side. And again, it just leads back to the connection of when you do the integral of a function, you're looking at the antiderivative of that function, right? Because if you have that capital F of x and you take the derivative of capital F of x, you end up back at this little f of x. And when you find the critical points of that little f of x, you end up finding where your relative max and your relative mins are for your antiderivative function. And if this is all just going over your head, the idea is this, right? In the past, I would give you a function f of x. To find out where its relative max and its relative mins were, you would find its critical points by taking the derivative and set it equal to 0, right? For this lesson now, I'm saying that if I have a function f of x, right, and I have its critical points, those critical points will tell me the relative mins and the relative max for the antiderivative function, for this guy right here, right? That's because if I take the derivative of that capital F of x function, I end up at f of x. And again, that's the big circle that I'm trying to get you guys around to see, right? The connection between derivatives and antiderivatives and integrals, as a matter of fact, right? So when you do the integrals of something and you're calculating the area underneath that curve, you're technically just looking for the antiderivative of that function. I know, long-winded speak, long-winded talk. Honestly, if you just wanted to go into it, it's basically what is Mr. Knocking trying to say? If I need to calculate something that looks like this, all I really need to do is look for the antiderivative of that function. So if I had something like this right here, the integral of 2x dx, and I was asked to evaluate that, it's just going to be x squared, right? If I was asked to find the integral of cosine dx, the integral of that is just sine squared. And someone sent me an email of a nice explanation of how they're supposed to memorize derivatives and antiderivatives of sine and cosine. And it was pretty neat. I believe it was done with like a chart. I'm sorry, I forgot your name. The email didn't have your name, but it had your last name. If you wanted to share who you are, who showed this to me, or you can correct me. They showed me this right here. I believe this is what they showed me. Negative sine of x, and this is negative cosine of x, right? Which is a nice chart to help you see where's sine positive, where's cosine negative, right? And where's sine positive and where cosine is. I just said that. Where sine is positive, where sine is negative, and where cosine is positive, where cosine is negative. But check this out. If you go in a clockwise manner, you can actually figure out what the derivative of the function that you're dealing with is. So if I was dealing with sine of x and I was asked to take the derivative of sine of x, that's just equal to cosine of x. If I was already at cosine of x and I was asked to take the derivative of that, I'd end up at negative sine. And if I was at negative sine, the derivative of negative sine ends up back at negative cosine, and it goes all the way around in a circle. Now that we've learned about antiderivatives, antiderivatives go in the opposite direction. So if I was at cosine, which I'm at right here, the antiderivative of cosine is equal to sine. You see that? The antiderivative of sine is equal to negative cosine. The antiderivative of negative cosine is equal to negative sine. The antiderivative of negative sine is equal to cosine. Little neat thing. Again, I'm going to just check my email. Somebody sent me that after the lesson, and I forgot who it was, which is a shame because I should give credit. For the yeah, see, it doesn't have your name pop up, but the student's name starts with the O. I can't say this person's last name. Ochoa. But yeah, that's the idea there. And hey, but yeah, this is very helpful, right? I think that's kind of neat. It's kind of cool that you can see that, and that is the connection between derivatives and integrals, right? All right, so that being said, let's go ahead and continue on with this lesson for the fundamental theorem of calculus. There's a couple of properties I need to show you guys. Properties. Let me see. Let me double check my attendance here. Maybe I don't think that student is in this. Oh, she's probably in my. I think she's in my period 4. That's why. Yeah, I think she's in my period 4. I'm gonna have to go thank her for showing us this. It's pretty cool. All right, anyways, let's talk about the properties now. Am I zoomed in enough here? I am, right? Okay. Properties of integrals. This is a very interesting idea, very interesting values that come out of it as well. If we do the integral from the bigger number to the smaller number, in other words, if I go backwards, right? If I do the integral from b to a instead of a to b, right? Of my function f of x dx, this is just going to be equal to the same integral from a to b, right, of f of x dx, but it's just going to be the negative value of it. It's just going to be the negative value of it, okay? That's the first property. If you switch the, I should know the name of this, the limits. They're not the limits. They have a name. You know what? This is gonna bother me. Integral name of A and B. I swear they have. The points A and B are called the limits of integration. I swear there's another name for this. Oh well, limits of integration. If you switch the limits of integration, we'll just use that for now. Around, it'll be the same area, and I hope that kind of makes sense, right? If you were to draw a picture from like, let's say A to B, remember the integral just means that you're calculating the area underneath this curve right here, right? It would be all of this area right here. And if I switch it around, you still get the same area. It's just negative because it's going in the other direction. That's all that is, right? I know it sounds weird to have negative area, but it's just basically putting a sense of direction on what we're dealing with, okay? All right, next property is if you take the integral and the limits of that integration is the same, it goes from A to A of this f of x function, dx, that's just gonna equal to 0. That's just gonna equal to 0. And hopefully that also makes sense because if I'm looking at a function that looks something like this, but I'm only taking it from A, I'm trying to calculate the area of this guy right here, right? That area of that right there has no width. It's going to go, I don't care what the height is, unless it's going to be f of A, right? So when I calculate that area, it has no width, which means that it has no area. That's why that's equal to 0. So if you ever do the integral of something from something to itself, that's going to be equal to 0, right? It doesn't even matter if you don't know what the function is. If I was doing, for example, right, I was asked, hey, can you evaluate this for me? The integral from 0, let's not do 0. I was looking for the integral from 3 to 3 of x cubed sine squared x to the 4th dx, right? And I was asked to do this. I don't know what the antiderivative of this is, but I do know that the area of this thing, no matter what this function looks like, is just going to equal to 0 because it's going from 3 to 3. Okay, so it's stuff like that, just to keep in mind. How often does that show up? Not too often, but if it does, you know, it's a very easy thing to calculate. All right, let's keep going. Let's keep going. Another thing that you could also take from this one is if there is a coefficient multiplying with your function. So if I have, for example, the integral from A to B of a constant multiplying with my function, f of x dx, that's just going to equal to the constant in front and then just doing the integral of the function itself, right? So that constant is like multiplying with your function, and you could just multiply to the area after you've calculated the integral, okay? That's like, for example, let's say I have here, what's a good example? Let's say I was doing the integral, right? Of, what's a good example for this? Oh, I know. Let's say I was doing the integral from 4x dx, right? What I'm saying is if instead of having a 4x dx, I can have this the same thing as 2 times the integral of 2x, right? Because 2 times 2 is 4 dx. And why would I do that? I have here the integral of 2x, and that's actually really easy to calculate, right? That's just going to be 2 times the integral of 2x is going to be x squared. So that way this comes out to just be 2x squared. You don't have to do it this way. Also, you could just go from here and just do this integral right off the bat. Some people prefer it. Integral of 4x would be 4 times, and the integral of x would be 1/2 x squared. But we'll talk about this later. Where is this coming from? There is actually a shortcut for calculating integrals, just like we have shortcuts for calculating derivatives. Power rule does apply into integrals, but we'll do that later. Why did you separate the 4 to a 2? Yeah, that's why this is a bad example. Let me retry that again. I was trying to show this property, that if you have a coefficient multiplied with a function, it's the same thing. I guess that didn't show it very well. But I was saying if you had, instead of 4x, I had 2 times 2x dx. I was trying to be clever about this. So that way when you rewrite it as 2 integral 2x dx, you can see that this right here looks like the warm-up we did, not the warm-up, the example we did earlier on Tuesday. Right there. That's why I was separating the 4 into that. But don't actually do that on the actual problem. I just couldn't think of a better example that explained why a coefficient multiplying with a function, you could just do the integral of that function. Oh, I'm an idiot. I'm an idiot. Hold on, here, I got you. There's a better example. Duh, knock me. Why don't you just use trig functions? Here we go. So if I had here the integral of 2 cosine of x dx, that's a better one. That makes more sense as to why bother splitting a 4 up into a 2 and a 2, where I could just write this right here. I can't multiply the 2 with that cosine, right? But I can integrate this by taking the 2 out of the integral and then dealing with the cosine of x dx. Oh man, that's a better example, isn't it? So then this right here, the integral of 2 cosine x is the same thing as the integral of cosine x by itself. This guy right here is just going to be sine x times 2. See that? This is going to be multiplying with that right there. I think that's a better example. Oof, sorry about that. That was not a good example. That 2 one is not a, you know what, let's just oh, this is already on record. Whatever. Let's just pretend that didn't happen. Yeah, there we go. I'm also too lazy to go back and edit this recording, so if you're watching this recording, you see that. I mean, it's not a mistake. It's just not a great example. All right, let's keep going. So you factored it out. Yeah, Monica, that's what I did. I factored out a 2, and just to prove a point, I guess. And I didn't really need to factor out a 2. I could have just thought of a better example, like this guy right here, and show that the 2 is a coefficient there. Oh well, it's not like I've been teaching this for multiple years, right? All right, the next one up for the properties that we're dealing with is, let's say I have 2 functions that are adding with each other or multiplying with each other, okay? Let's go a little bit further down. I don't have enough space here, hold up. I know this isn't that big of a deal, but I like having things fit in the correct spot. So I'm gonna just move you up here. There we go. All right, so the next property is going to be the integral from a to b. And if I have 2 functions adding together, right? If I have f of x adding or subtracting to g of x. So these are 2 separate functions, right? dx, right? This right here would simplify out to the integral from a to b of f of x plus f of x dx plus or minus the integral from a to b of g of x dx. And what I'm saying is if you have a plus or a minus sign separating things out, you can do each integral individually. You don't have to do it as one clump of a thing. It's the same thing when we did derivatives, right? If I had x squared plus 3x and I was calculating the derivative of that, I would just use the power rule for each of those functions. And that's kind of the same thing here. If I was looking at, let's say I had here the integral of, let's say, cosine of x plus sine of x dx. What I'm saying is this is the same thing as if I were to do the integral of cosine of x dx plus the integral of sine x dx. And then I would just do these guys individually, right? I just do these integrals individually. Does that make sense? Like that is a property that you are allowed to do with these integrals. Now that we know what an integral is, there are these different properties that we can apply to them. And then of course there's proofs for these guys. I'm kind of rushing through it and not showing you the proofs, but that's the idea there. Okay. Last but not least, if I have the integral from a to b of a function plus the integral from b to c of the same function, right? Why, that's just going to equal to the integral from a to c of that function. Right? And that one doesn't require too much thinking about it, but if you wanted to see it, if I had this function f of x, like this is my f of x, right? And I was adding the area from a to b, that would be this area right here, right? And then I do the area from b to c, which is from here to here. Hopefully you guys can understand that if I were to add up from a to b, along with b to c, it's the same thing if I just were to add it straight up from a to c. You know what I mean? So it's the same thing. So if I went from here to here, it should be the same from there to there. That's a terrible color. Does pink look better? No, it doesn't. Blue? No. All right, it doesn't matter. You get the idea, right? You add those two together up from, if I'm going from, whatever, from A to B, that's this area right here. And then if I add that up with B to C, that's this area right here. And then if you add them together, we just end up with that new one right there, which is going to be from here to here, the whole area. All right, those are some basic properties there. Okay. Now, I haven't shown you actually how to evaluate it if it's from a to b of an integral. I've only told you that if you do the integral of a function, we get this thing called the antiderivative. I'm sorry, I didn't mean to scroll there. You guys are probably still copying that down. But this is the last part right here. This is what this is like the main thing I take away from the fundamental theorem of calculus, which is basically how do you evaluate the integral from a to b of f of x dx? And most of the times, I just use a calculator to do it. You guys have seen it on the TI calculator. It's fn int, or option number 9 under math. And you can let it do it. But on the AP exam, you're going to have a section of your exam where you're not allowed to use your calculator, which means you need to know how to evaluate this without a calculator. Right? So when you need to do that, this is going to equal to the antiderivative of f of x evaluated at b minus the antiderivative evaluated at a. Some people don't like writing this whole thing out like this. Most books define it to say, oh, f of x dx is the integral of that is going to equal to the antiderivative of it, so this capital F of x, evaluated from a to b, right? That little line right there, it just means to evaluate. Evaluate from such and such to such and such. And yeah, let's do an example. Let's do a quick example here. You ready? Are you guys able? Were you guys able to copy all these properties down? Hopefully you guys were. I'll leave it there for a little bit. Yes, just give it a second for some people. A little bit slower than others. All right. All right, so this is right here. This is the property we're going to be focused on right here. This for this next lesson right here, or not the next part of this lesson. So let me go ahead and zoom in a little bit here, and let me show you an example to do here. So let's take a look here. Let's say I was asked to evaluate. That's a gigantic V. Evaluate, right? Let's say I was looking at the integral from 0 to pi, right, of cosine x dx. Okay. Now we can't, like I said, we can just use our calculator to do this, right? It's not a hard thing to do. Which, by the way, I want you guys to practice this, even though I want you to do both. I want you to do it by hand, and I also want you to use your technology to do this. And if you haven't done so already, right, get a TI emulator, because the TI calculator is going to be available on the day of the exam, and you will need to know how to use this. And I won't be there to help you to tell you what functions you need to press. So it just comes from repetition. You practice this over and over again. So on the calculator from the home screen, if you press math and you go all the way down to option 9, right, you'll have fn int, which is the integral of it. If you have a different calculator, actually, let me show you this one first. So this is going to go from 0 to pi of cosine of x, and then we have to put the dx at the end there. And the place I pushed the x, someone asked me this earlier, is this button right here. This is your variable button. It's default to x, but if you wanted to go into settings, you could change it to like t or theta or whatever it is that you need. But anyways, it's default to x right here. And then I go ahead and press enter, and I get this number right here. Negative 3.2 times e to the negative 14. That means there's like 14 decimal places there. So this is a very small number. In fact, it's so small that I believe this is going to equal to 0. Remember, your calculator does integrals by estimating. So this one actually doesn't. I would just do this one by hand and see, like, is it possible for me to calculate this itself? Let's take a look at it. So when I'm dealing with the integral of cosine of x, remember, cosine of x is the function that we're looking at right here, right? The function that we're looking at. If I'm looking for the integral of this, all I really need to do is find the antiderivative of this, right? This right here is the antiderivative of that, right? So what's the antiderivative of cosine? I'm asking myself, what do I take the derivative of that will get me this cosine? And we saw earlier with that nice little shortcut that the derivative, the antiderivative of cosine is going to be sine of x, right? Sine of x. So when I'm doing this integral right here, this right here is equal to sine of x, but is going to be evaluated from 0 to pi. from 0 to pi, right? Now, that's right. This is right here. This is what I'm hoping you guys can see. This 0 right here is like our A. That's going to get plugged into here. And this pi right here is like our B, which is going to get plugged into here. So this thing right here is equal to, you ready? Sine of pi minus sine of 0. That's all it is. Pi goes there, 0 goes there. And then we just evaluate these guys. Hopefully you know your trig values, right? Have you memorized your trig values? If not, man, we didn't have enough time for this. You need to know your basic trig values. I feel bad, though. We haven't had the time to practice this, so me expecting you to know it is basically asking you should have learned this last year, but at the same time, last year we went through the beginning of the pandemic. I'll try to get you guys something that will help you practice this, because you do need to know, this is just pi, by the way. You should know what sine of pi is, right? Sine of pi is just equal to 0. Sine of 0 is just equal to 0. So 0 minus 0, my answer for this is just 0. Do you guys know pi over 2, pi over 3, pi over 4, and pi over 6? Do you know those values? You need to know sine of that, and you need to know cosine of that. And I just realized that right now. We have not practiced those values. Sine and cosine of those basic trig functions around the unit circle, you should know. I know maybe you might have been like given a cheat sheet or something, but yeah, I'll figure out something. Maybe we'll do something that'll get you guys to learn it. It might have to be on your own time, but it's not that big of a deal. It's not that important. Yeah, Jeffrey, I'll be honest with you. I never memorized the unit circle myself. When it came down to the test, I drew the thing out instead of. It's a lot easier if you memorize it. What is the unit circle? I don't know if you're joking or not, but I mean that is a valid question, Calvin, because some people actually don't know it and did not learn it. I was taught to memorize it, and I never memorized it because I would just construct it from memory instead. So it's this guy right here. So if you're looking at something like this, the x values is your cosine value. So this right here is saying cosine of pi over 6 is equal to the square root of 3 over 2. Cosine of pi over 4 is equal to the square root of 2 over 2. Cosine of pi over 3 is equal to 1/2. And then the y values are your sine values. And you're supposed to know these from 0 all the way around to 2 pi. Like I said, I never memorized this. So once if someone asked me, hey, what's cosine of 7 pi over 6? I didn't have that value ingrained into my head. Oh, it's negative square root of 3 over 2. Yeah, time test, you would fill out the whole circle. Yeah, I did. Yeah, that's a normal thing. That's a normal thing. And my problem with that is it's great for that year, but normal students, I shouldn't say no, that sounds mean. On average, most students forget it, over summer. And I was one of those students. Once I got to calculus, I was like, what the heck? Oh God, this sticks with you. And I just want to let you guys know, this sticks with you throughout, like, if you go into engineering, it sticks with you like for forever. So I'm trying to think right now, maybe not memorizing it, but maybe come up with a mnemonic or come up with a system for yourself to come up with these values. Like I said, I never memorized cosine of 7 pi over 6. What I did instead was realize that 7 pi over 6 was the same same location as pi over 6 using coterminal angles. I don't know if you guys can see this or not. Let me click on this and make that a little. Oh, that's terrible. So what I would do is I would just say like the distance from 7 pi over 6 to pi, this thing right here is a difference of about pi over 6. So I just kind of like memorize, I learned these 3 values right here. And then if you look around the unit circle, they're the same values all the way around. And I kind of just constructed it based off of that. And then your teacher might have taught you this as well. Right, to tell you which trig functions are positive, which trig functions are negative. In the first quadrant, all trig functions are positive, right? In the second quadrant, only sine is positive. In the third quadrant, only tangent is positive. And in the fourth quadrant, only cosine is positive. And they might have taught it to you as like all students take calculus as a mnemonic to remember it. I remembered it as all strippers take cash to help me remember it. Sine here, tangent here, cosine, and this is all, right? But either way, we'll set this aside. You're gonna have to at some point learn these tangent values or these trig values for this unit circle. Okay. Oh, by the way, so this calculator didn't come through for me, did it? It's saying that on the calculator, right? On the calculator, we got that this is approximately equal to, and this is, by the way, this is what this would look like: 3.211 with 14. So it should be 13 zeros there. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 3, 1, 3, 2, 1, 1. So that's what the calculator is telling me. It's a very, very small number, right? But we know that the actual value is supposed to be 0 if we just know our trig values. So there are limitations to your calculator, and that's because this integral, remember, the idea of an integral is that you have infinitely many rectangles from A to B, and you're just summing up those areas, right? The calculator can't do infinity. Instead, they do, I believe, like 10,000 rectangles in between the numbers that you have from A to B. So it has about 10,000 rectangles between there. And with those 10,000 rectangles, it tries its best to calculate this out. Sorry. But again, if you take a look at this, right, the original function f of x is the cosine of function, right? So if I have here f of x is equal to cosine of x, right? Cosine function looks like this. Man, I'm good at drawing, aren't I? So it's going from 0 to pi, and pi is right here. So when you calculate this area, you're technically calculating this area right here, which is a positive area, all the way to here, which is a negative area. And the reason why it comes out to 0 is those areas are perfect. They match up perfectly to each other. So I have a positive area plus a negative area. That's why the answer is 0, right? Graphically, that's why the answer is 0. Analytically, why the answer is 0 as well, because, you know, sine of pi is 0 and sine of 0 is 0. 0 minus 0, 0. All right. Let's keep going. Let's try another one here. Let's say I have here. Let's say I was asked to do the integral from 0 to pi of sine x dx. What do you guys think that's going to be? If you had to guess, what would you think that value is going to be? Just a guess. What do you think? I just realized I need to change the light bulb in this room because the sun just got covered by a cloud and my room got dark and I got paranoid that I was going blind. Anyways, any guesses? No guess? It's fine if you don't have a guess. Negative cosine of it. Okay, yeah, all right. So we're going with the analytical part of it. Let's do it, Brian. So yeah, the integral of sine x dx is going to be negative cosine of x. Very good. Very good. That is exactly what it is analytically. I was just trying to see if anyone had a guess for the area itself. But let's do it. Let's actually calculate this out. So it's negative cosine of x, and we're going to evaluate this from 0 to pi, right? From 0 to pi. So how do we evaluate this? Why, this is going to be equal to negative cosine of pi, right? Minus negative cosine of 0, right? Remember, when you do the integral and you're evaluating this guy, right? I should write this off on the side somewhere. If you do the integral from a to b of some function, f of x dx, right? This is equal to f of b minus f of a, right? So this minus sign right here is not part of the negative cosine. That minus sign right there is telling me to subtract those two values. Is this also 0? That's where I was trying to go with, Monica. That's what I was trying to ask. That's what I was trying to bait you guys into saying. I was trying to bait you guys into looking at, like, oh, is this also going to be 0? And I don't know. It kind of seems like it should be because, you know, sine and cosine look like they're related up here. But it's not. It's not. And Brian's saying, is it 2? Well, let's take a look. Cosine of pi is what? Do you guys know? This is going to be negative, whatever the heck cosine of pi is. Cosine of pi is negative 1. Very good, very good. And the way you know that is cosine pi is the 180 angle, so it's going the other direction. And cosine just gives you the x values of that. So cosine of pi is negative 1. So we have here negative 1 minus negative. What's cosine of 0? Cosine of 0 is just 1. Cosine of 0 is just 1. Man, I got a lot of negative signs going on here. So let's take a look at this carefully here. Negative 1, that's just 1. Negative minus a negative 1, that's also just a plus 1. So it does come out to be equal to 2. Ryan, looks like you were right. The answer here is 2. And let's take a look at this graphically. Let's take a look at this graphically. I love looking at things graphically. They just make more sense that way. If I was graphing out sine of x, you guys would agree, right? Graph of sine of x starts at 0, goes up, then down, then back to 0. This completes the cycle after 2 pi. I'm not going to go all the way to 2 pi, though. I'm going to go from 0 to pi. So from 0 to pi, the area underneath this curve is this area right here. So if I was going to go from 0 to 2 pi, chances are that would be 0. But from 0 to pi, it's just this positive area right here. This positive area right here. And it turns out, this positive area right here, why, that's just equal to 2. Ta-da! All right, guys. I want you to try 3 problems here. I want you to try 3 problems. Okay? So let's see how you guys are going to do with this one. So let's go ahead and have you guys try these 3. Okay? Let's see how you guys are. So try this out on your own. Try this out on your own. 3 problems right here. Let's go with number 1 right here. I'm going to ask you to find. You ready? Can you do the integral without a calculator? Do this without your calculator just for now, just to see how it is. See if you can do it without your calculator. And then if you don't get it, you can try it with your calculator afterwards just to see what the answer is. But try these ones without your calculator first. The integral from 0 to 3 of 2 dx, right? That's going to be the first one I want you guys to try. Number 2, I want you guys to try to find the integral from 1 to 3 of x dx. And then the third one I want you guys to try on your own is going to be the integral from 0 to 2. This one's going to be a little bit difficult. X plus 3 dx. Can you guys go ahead and try these 3 problems? I'm going to go ahead and set a timer for, let's go 3 minutes. A minute a problem. That should be fine, right? A minute a problem. So let's go ahead and set a 3-minute timer. I want you guys to go ahead and try this. And yeah, let's see what you guys get. Try that out. Try that out. No Pear Deck on there for right now, I guess, but for you guys to try it. Ooh, that's a good idea. While you guys are doing that, I'm going to get some candy. Dog? Can you hang out in the doorway, dog? All right. Oh, I have a minute. Do I have a minute to eat this candy? I think I do. Nah. Oh, you have. Let's see here. Just double checking. I'm missing 3 students today. Julia, Ilias, and Alejandra. All right, if you're here, let me know. Just double checking attendance. Oh. Oh my. All right. I forgot to set up the pear deck. I wish I could see what you guys have as your answers, but then at least this way you don't have to do it twice, you know, doing it on the pear deck and then doing it on your notes. Man, though, it makes it sucks. This makes it a little bit crappy that I can't actually check your work, but we'll see. Let's see. Let's go this one. Let's throw this one out right here for number 1. Right? What is the antiderivative of 2? Can somebody help me out here? Somebody help me out here. What is the antiderivative of 2? Monica, Brian is going out. It's 2x. 2x. And if you're having trouble seeing, how did they get 2x? The question is asking what function, when I take the derivative of, I would get to 2. So if I take the derivative of 2x, right? If I take the derivative of 2x, right? I should get back to 2. That's where that is. So if you're, it takes, make sure that, you know, you have your skills with your derivatives up and ready to go. It'll help you out really well on this section of the integral section. Anyways, so this is it, right. 2x is going to be what the antiderivative of 2 dx is. And I'm going to be evaluating this from 0 to 3. It means I just have to plug in those values in for x. So this right here is going to be equal to 2 times 3 minus 2 times 0, which is just going to come out to be 6, right? That's it. That's your answer. So the integral of this guy right here, the integral from 0 to 3 of 2 dx, that's just equal to 6. Okay, that's it. That's it. Easy, easy. Let's go to the next one here. Who was able to figure out the antiderivative of x dx? 1/2 x squared. Very good, Brian. Very good. 1/2 x squared. If I take the derivative of x squared, I get 2x. 1/2 of 2 just becomes 1. They cancel out. So that's how that ends up as x dx. That's perfect. 1/2 x squared. And it's going to be integrated from 1 to 3. So we just plug these values in. There's going to be 1/2 3 squared minus 1/2 1 squared. Notice the 1/2 has to go along with it when I'm evaluating there, right? It has to go with the 3 and the 1, right? Excuse me. Oh. When I plug in these values here, 3 squared is going to be 9. 9 over 2 minus 1 over 2, which is going to give me 8 over 2, which in other words just gives me 4, right? And again, you can always double check this if you're just doing this for homework, right? Again, I want you to practice your calculator. Don't think like, hey, I'm in a math class, I shouldn't use my calculator. I want you to practice this. So we're going to go ahead and go math 9, and I'm going to practice plugging this in. This is going to go from 1 to 3 of x dx, right? We plug it into the calculator, and it gives us the value of 4. Hey, look at that. That one actually gives us the exact value. So it looks like it matches up pretty well there. Matches up okay there. All right. This one's going to be a tricky one. This one's going to be a tricky one, right? The integral of x plus 3 dx. Remember, the property that you're allowed to use, you can split these up with an x and the 3x. And that looks like exactly what Monica did. If I was only focused on this x right here, the antiderivative of just x, we got that over here, didn't we? We found out that that's going to be 1/2 x squared, right? And then we just add that to the other function being 3, right? It's kind of like that 2 right there, isn't it? But it's a 3 instead. So the integral of 3 would be 3x. And that's your antiderivative of x plus 3x. I'm sorry, antiderivative of x plus 3. You end up with 1/2 x squared plus 3x. Evaluate this from 2 to 0, right? And then now we just plug these in. This one gets a little bit more complicated, guys, when you start plugging it in. We have here 1/2 2 squared plus 3 times 2, right? This whole thing right here is me evaluating it at 2, right? That's this guy right here, okay? Minus 1/2 0 squared plus 3 times 0. Right? That whole thing is me evaluating it at 0. And remember, you have to subtract these two. Okay? So this right here is going to be 2 squared, which is 4. 4 divided by 2 is just 2. Plus 6, that's this guy right here. Minus, this is going to be 1/2 of 0, which is 0. Plus 3 times 0, which is 0. This looks like this is just going to come out to be equal to 8. 8 is our answer for this one right here. Right? And that's it. That's it. That's the idea there. Okay, that is the idea there. Like I said, these problems get easier the better you are at knowing what your function should have looked like when you take the derivative of it. And let me show you one last example of that. before we move on here. But that one last example is going to be this guy right here. So these weren't too bad, right? But sometimes some people will get stuck when they see a problem that looks a little crazier than this. And let me show you one. This one right here is going to be the integral from 0 to 1 of 1 over the square root of 1 minus x squared dx. Your mind might be rushing through some different techniques that you need to go through, but this one actually is a very, very straightforward one if you know, if you have the idea of what the original function should look like. You don't need to do any techniques, any steps on this one. You just need to know what the antiderivative of this one is. And that's one of those things, just like, if you don't know it, then you're going to struggle with this, is what I'm saying. I struggled with this a lot. I always have trouble memorizing this one. I was always trying, like, how do I integrate this thing? I can't break this up into two fractions. I can't separate it. I can't do the integral of the square root and that x squared. Someone already beat me to it. Brian's already seeing this right here. This right here is the derivative of the inverse sine function, right? The derivative of the inverse sine function is equal to 1 over the square root of 1 minus x squared. See that? Now, my technique when I first learned this, I would always try to be like, oh, this is the same thing as, this is going to be like 1 minus x to the 1/2 over 1. And there's no real, and then if I rewrite that again, this is the same thing as x squared, I should say. This is the same thing as 1 minus x squared to the negative 1/2. And I try to do this using the chain rule. We don't know the chain rule yet for integrals, so we can't just go ahead and do that. And I also can't distribute that. So that's not going to work. And actually, that gets way more complicated than need be. Remember, the trick for this thing is if you're doing integrals, try to think of the function that you take the derivative of, and you'll end up here, right? You end up here. And if I take the derivative of sine, inverse sine, or arc sine, that's how I end up there. So this right here would just be equal to the inverse sine of x, evaluated from 0 to 1. That's it. And then you just plug this in. This is going to be inverse sine of 1 minus the inverse sine of 0. Which, by the way, I know I was giving you this whole hard time about memorizing the unit circle. It comes up this way too. You need to know it backwards. You need to know what the inverse sine of 1 is. But this is saying sine of what would give us 1. And I hope you guys know that sine of pi over 2 would give us 1. Sine of pi over 2 is equal to 1. Minus sine of what would give us 0. There's two values there. You can either say sine of 0 or you can say sine of 2 pi, right? You can go with either one. In this case, though, I'm going to go with 0 because it's just easier to start there. So pi over 2 minus 0, that's going to equal to pi over 2 as our answer for this one. I know, guys, it's a little strange, a little weird, but I promise you, you'll get the hang of this. It's going to be like, when you first learn derivatives, it seemed kind of crazy. But now if I were to ask you, hey, guys, what's the derivative of x to the 5th? You would tell me 5x to the 4th. You're going to do the same thing with integrals. It's just going to take a little bit of time and a little bit of practice, I promise you. Some of you guys are going to look at this like, how the heck am I supposed to know what what the integral of 3x squared is? I know it sounds complicated, but a couple of you guys have already clicked in your minds and said, oh, that's just x cubed. It just takes time and it takes practice. So don't get frustrated. Take your time with it. Do the problems. Do the practice problems along with it, and you'll get there. And if you're not, come ask me for help. I'll try to get you set up and ready to go. All right. That's it for the fundamental theorem of calculus. I do have the next set of notes. It's also going to be guided, so I'm going to give you the link right now. We're going to go from definite integrals to Riemann sums, and then Riemann sums to definite integrals. That's what this is saying right here. So let me give you the link for this guy. These are guided notes that we're going to do together. And then you can just submit it once you've finished it. Let me go ahead and take a look at it here. So I gave you the link. You guys can open it up through Cami. You guys can fill it out along the way on Cami. You do not have to have it on your own notes. This is just something for you to practice. So remember, when we first learned about this integral notation, right, I taught you guys that it actually comes from the idea of calculating a bunch of areas underneath the curve, right? And that areas underneath the curve, like if we use LRAM, RRAM, or MRAM, right? If I had 8 rectangles, 20 rectangles, those are all estimates. If I can get myself to get to infinitely many rectangles, right? That's this guy right here, infinitely many rectangles. And I took the limit as I approached that infinitely many rectangles. We found out that that's equal to this integral, which gives us the exact value. That's the calculus approach of this, right? It's the fact that we're taking the limit as we go towards infinitely many rectangles, right? We can calculate the area underneath the curve using this. Well, it turns out we need to be able to go back and forth with this. So this is the guided notes for us to do that right here. I want us to practice this because these are easy points usually on the AP exam in the multiple choice section. They'll give you a problem that's written in limit notation, and they'll ask you to evaluate it. And if you're like me, you might look at it and go, what the heck is that? And miss out on easy points. So what I wanted to do instead is not have you be like me, but instead realize like, oh, they just want us to write the integral if you see this limit notation, right? Because the hard part I had of visualizing this was remembering that this is the height of your rectangle, right? If you just picture it that way, this right here is the height of a rectangle, H-E-I-G-H-T, right? And this right here is the width of your rectangle. And you're just multiplying them together, right? When you multiply them together, that gives you the area of a rectangle. The summation notation tells you to add up all of those rectangles. So if you can picture in your mind infinitely many rectangles and you summing them all up, that's what the integral is, right? And so when you see a problem like this on an exam, you should be thinking the integral from A to B of a specific function that you're dealing with, and that function tells you the height. Now, this is going to look a little bit crazier, okay? This is going to look a little bit crazier here, and that's right here. The concept, when you're taking the integral from A to B of f of x dx, you're doing this idea of summing up rectangles infinitely. And this right here, I'm going to break it down for you. This right here is using the right-handed height. So it's RRAM, right? It's the right rectangular approximation method, but we're doing it for infinitely many rectangles. You see that? The limit as n goes to infinity, the number of rectangles is going to go from 1 all the way to infinity. And this right here, this is the width, b minus a over n. That's our delta x. I told you guys this earlier, right? It's how wide do each of these rectangles need to be. The width of these rectangles have to be how far it is from b to a, divided by however many rectangles you want. Just a real quick example. You don't need to write this down, but I just like showing this to you guys. Again, it's under Riemann sums right here. Let's open this graph. And I'm hoping that you guys can see this right here. If I have, if I'm going from 0 to 3 and I want 3 rectangles, the width of these rectangles, right? If you guys can see it, the width of these rectangles go from 0 to 1, 1 to 2, 1 to 3, or 2 to 3. The widths of these rectangles is exactly equal to 1, right? That's because 3 minus 0 is 3 divided by the number of rectangles, which is 3. 3 divided by 3, 1, right? It gives you a width of 1. If I increase the number of rectangles to 6, right? There's 6 rectangles now. 1, 2, 3, 4, 5, 6. The width of these rectangles are now 3 minus 0, which is 3, divided by 6, which is now 1/2. So the width, the delta x's, is equal to 1/2. So as I increase my n, right, it decreases the width of each of these rectangles. So as I approach infinity, right, the number of rectangles, of course, go towards infinity, but the widths of each rectangle approaches 0. It gets smaller and smaller, but they get smaller and smaller in unison. Do you see that? They get smaller and smaller in unison. This right here, the width of these rectangles, that's an ugly number. Let's go to a nice number. Boom. The width of these number is by 0.1. You see that? It goes 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 3. That's because n is equal to 30 here. So 3 minus 0 is 3 divided by 30. You get 1 over 10. And this is going to go all the way up to, let's go to 90. Let's see what that looks like here. Boom. So if I have these really small boxes right here, these widths, oh, they're not nice widths. They're stopping at weird numbers, but you get the idea, right? That's the idea here. So when we're doing these notes right here, right, I'm telling you, I used to struggle with this. Whenever I saw these limit problems, I was like, what the heck is that? I just need you to get into your mind. It's just the integral. It's just the integral. Okay. All right. So here's the step-by-steps. I'm giving you these out so you don't have to write these. Okay. When you're doing this and you're converting a Riemann sum into a definite integral, right? The first thing you need to do is to be able to identify what your delta x is. What your delta x is, right? Your delta x, remember, is just the width of your rectangle. And the width of your rectangle is just calculated by the limits, b minus a, divided by however many rectangles we want. And of course, we're looking at it approaching to infinity. So we're just going to leave it as n, right? We're just going to leave it as n. Identify delta x as simple as finding a constant divided by n. It is generally separated from the rest of the expression and often sitting by itself at the end. So that's the hint that you should use to calculate or to identify your delta x. Step 2, determine x sub k by using the formula a plus k times delta x. So if you're confused by that, that's right here. That's inside here. That's the idea that you're evaluating your function at this specific x value. So a is where you start, right? If you start at 0, that's what your a is going to be. But then you're going to add how wide your rectangle is. And the way you add your rectangle is what number rectangle you're on times the width of these rectangles. But of course, remember, they're going off to infinity. So we're just using this as a placeholder to help us to do that, right? To find x sub k, look for an expression that looks like a plus k times delta x. Determine b. At this point, you already know a since it shows up in x sub k. And since delta x is equal to b minus a over n, you can quickly determine the value of b. I'll show you this work. I just realized these stuff sound a little bit more complicated than need be. So let's actually just get in there and do some of these, okay? Let's go ahead and do some of these. So let's go ahead and let's take a look at one of these examples here. Okay. Actually, let's finish this off. Rewrite the sum using x sub k and delta x. So a plus k delta x is equal to k of x. I'm saying x of k. B minus a over n is equal to delta x. Rewrite the integral by making the following changes. X sub k as an x function, delta x as a d of x. This summation from k is equal to 1 to n into an integral of f of x dx. Let's just look at a problem here. This one's already done for us. I'm going to go ahead and highlight this through here for you. All right, so step 1. Let's take a look at step 1. Step 1, determine delta x. Remember, the trick to find out what delta x is you're looking for something that's divided by n that's sitting by itself, right? So take a look here. Do you guys see the delta n here? The delta x. The delta x is sitting by itself right here on the outside. Delta x is going to be equal to 3 over n. You guys okay? 3 over n, right there. Part 2, right? Look for x sub k. Or x sub I. They're dummy variables, by the way. They're just placeholders. X sub k, x sub I, right? So look for something that looks something like that. And that's going to be right in here. I don't know if you guys can see it. Right? This guy right here. We're looking for something that looks like this, a plus k, and then it needs to be multiplying with delta x. Well, there's my delta x right there. My a plus k. That looks like it's this guy right here. So just a real quick question here. That a plus k times your delta x looks like it's inside that parentheses, right? It's inside the parentheses that's being raised to the 5th power. So what's your a equal to? Your a is just equal to 1. Your a is equal to 1. So now we know, if I were to write this integral problem, I know what the a value is. It's starting at a equals to 1. Okay? Knowing that a is equal to 1, you can actually find out what b is equal to. You ready? Since I know that delta x is equal to 3 over n, and I also know that delta x is also equal to b minus a over n, I can set them equal to each other. The n's right here, for fractions equal to each other, I can just go ahead and say that b minus a is going to equal to 3. So now that I know that a is equal to 1, if I plug that in there, b minus 1 is equal to 3. I know that b needs to equal to 4. So I have now my a value. I have my b value. I'm almost done with this problem. You ready? Remember, a plus k times delta x, right, is the same thing as x sub k. That's this guy right here. This whole thing, if you know that that is a plus k times delta x, that's just your x sub k. So I'm going to replace that with that. I also know that 3 over n is the same thing as 4 minus 1 over n, which is the same thing as b minus a over n. That's horrible writing, Nakmi. Can you make that a little bit neater? B minus a over n. That's just as bad. So I can say that this right here is the same thing as this right here, b minus a over n. But remember, b minus a over n is the same thing as delta x, and that's what this is right here. So I'm going to replace that with that. So instead of looking at this crazy thing up here, I'm going to rewrite it as this. Once you rewrite it like this, you can actually see what the original function was. The original function is x to the 5th power. So when I do that, I can now rewrite this crazy limit as a definite integral, because I know that a is equal to 1, b is equal to 4. So I'm going to be doing the integral from 1 to 4 of the function I'm dealing with, which is x to the 5th. Instead of delta x, I write it as a dx, and that's my answer. That's my answer. So I kid you not. I kid you not. I still remember on the AP exam getting this as a multiple choice question and looking at that and going, what the heck is that? And in reality, all I needed to do was do the integral of this and evaluate it from 1 to 4. And I'm still a little salty. I was like, man, that could have been an easy point. But, you know, I didn't know it. I didn't learn it. I didn't study enough, right? So now I'm showing it to you guys. Hopefully you guys will see it and you realize, like, this looks more complicated than it is. It's actually just this written in a different form. And now that you know how to evaluate integrals, it's actually not too bad, right? Like, what's the antiderivative of x to the 5th? Well, we'll talk about that later. We'll deal with that later. So let's do another problem here. Let's practice one together. Okay, let's practice one together here. So looking at this closely, before I go into it, most of the times when I do these types of problems, I like to see if I can try to guess what the function is going to be. In this particular case, it's a little hard to see, but hopefully you guys were able to see that f of x in this particular problem was equal to x to the 5th, right? Is equal to something to the 5th. You can kind of almost visually see that it's some stuff being raised to the 5th power. So when I come down to this problem right here, I kind of like to take a guess. I'm assuming, I don't actually know if this is true or not, but I like to guess it. And I like to guess that f of x here, I kind of think the function is going to be something square rooted. I don't actually know if that's going to be what the function is, but that's what I'm guessing because I see the square root function here, right? That 3 plus 2k over n stuff, that might be my a plus k. It might be. So we're going to go ahead and figure that out. So let's go ahead and look at this and let's see if we can determine what our delta x is, right? Remember, our hint for delta x is something divided by n, usually by itself at the end somewhere. I don't know if you guys see it. Do you guys see it? I'm going to write that down. My delta x right now is going to be equal to 2 over n. That's my assumption so far. Okay. Next thing up, I'm going to determine my x sub I. My x sub I is usually something that looks along the lines of a plus k times delta x. A plus k times delta x. Well, I have something that has a plus k in there that looks like that, right? It's this 3 plus 2 over k, 2 times k over n. But it's not quite what I want. I want a plus k by itself multiplying with the delta x. Well, I can kind of see the delta x is right here with this 2 over n. So I need to do a little bit of a tricky maneuver here and rewrite this as, you ready for this? I'm going to rewrite this as 3 plus k, combine that together, times 2 over n. Can I do that? Is that okay? What I'm essentially doing is rewriting this as k in front, and it's multiplying with 2 over n. Right? I should not put parentheses like that. That's wrong. 2 over n. That's better. Right? So it's not distributing to the 3. It's just rewriting that k so that's in front right there. So that way, this looks like it's a plus k times delta x. You see it? So what's my a value, guys? What is my a value equal to in this problem? A is equal to 3. So right off the bat, I know that when I do my integral, it's going to be the integral from 3 to something, right, of f of x dx. I've already figured out what the a is. And all I did was just do a little bit of rewriting, and I found out that this 3 is by itself right here, and that 3 by itself, that's my a value right there. Now that I have my a value, I can determine my b value. You ready for this? Remember, b minus a over n is the same thing as, in this particular case, 2 over n, which implies that b minus 3 should equal to 2. So what does b have to equal to? Solving this for b, I end up with b is equal to 5. I now have my end result for my integral. So this integral is going to go from 3 to 5. It's going to go from 3 to 5. We're almost there. We're almost there. Rewrite using x sub k and delta x. So this right here is going to be the limit as n approaches infinity of the summation of k equals to 1 to n of, instead of, it's going to be the square root, but instead of 3 plus 2k over n, I'm going to write that as x sub k. Instead of writing it multiplying with 2 over n, I'm going to write that as delta x. We're almost done now. Replace the limit as n goes to infinity of the summation as k goes from 1 to n as the integral from 3 to 5. I got that right here from this 3 and this 5 times the function, the square root of x, and replace the delta x with a dx. And that's it, guys. That's your answer. Ta-da! We're not going to evaluate these for this notes. I don't know why I just quoted that. We're not going to evaluate these for notes. We're just going to practice going back and forth on this, right? So on this right here, don't think of this as homework. This is just for you to practice. You will need to know how to write back and forth from a limit definition into a integral function. And just to show you that it is not homework, you should have solutions on there. You should have the answers down here from 1 to 10. So, you know, I suggest practicing these. And then if you don't feel like it, just copy down the answers and put it here and then hit the submit button. This isn't due until next week, but this is just something that you need to practice. It's a very quick thing to do, to go from limit notation to integral notation. So you go back and forth. That's going to be part of your homework. In your homework, though, they might switch it up. They might not use x sub k. They might use c sub k. And just think of that as a dummy variable. It's the same thing as x sub k. They're just using c instead. So don't let that trip you up when you guys take a look at the homework. Actually, let me show you that real quick. I know someone is going to look at the homework and just be like, those are different, knock me. Why didn't you not show me the c instead of the x sub k? And traditionally we use x sub k. The homework just writes it as c sub k for some reason. So let me show you that real quick. So here's your homework. It's these numbers right here, numbers 1 through 7, 10, 13, 14, 15, 22, 23, 31, and 32. 1 through 7, if you take a look here, they're asking you to rewrite it as a integral notation. So right here. Oh, wow, this is actually a little bit easier. You don't even need to find your a and your b. They actually just give you your delta x here. So right off the bat, number 1 right here, the limit as n goes to infinity of the summation from k goes from 1 to n of c sub k squared delta x. And they want you to do it from the integral from the values from 0 to 2. Do you guys see what this is, by the way? Let me just copy this right now. So for your homework, I'm going to give you guys number 1 right now, just to let you guys have it. Let me scroll down to the bottom here. So from your homework right here, right, number 1 is asking us to rewrite this as an integral. I hope you guys can see that this integral is just going to be the integral from 0 to 2. They give us it, of x squared dx. And that's it. This is easier than the ones that we were doing in here. So 1 through 7 should be easy for your homework. Practice doing it with my notes. Honestly, you should just practice with these guys. If they give you a Riemann sum, that's what number 1 is, write it as an integral. If they give you an integral, try practice writing it the other way. Try practice writing it the other way. So for example, right here, number 2, they give you the integral from 1 to 5 of f of x dx. To write that as a Riemann sum using the limits part, the limits definition, it should look like this for number 2. So, you know, go from integral back to that. Sorry, let me go back to number 1. There you go. And that's the idea there. Okay, so with what I've shown you so far, you should be able to calculate all the problems for your homework for this section. you should be able to write back and forth between limit definition to integral. And if I give you an integral, you should go back to be able to write me the limit definition. And you should now be able to evaluate definite integrals, right? If I ask you to evaluate this one right here, you should be able to do this right here. So I will ask you to evaluate the integral from 0 to 2 of x squared. So what's the antiderivative of x squared is what's being asked there. And yeah, that's going to be it from me today, guys. I think that's it. You guys have homework now to work on. Practice the notes. You can just, just copy the answers here and put it up here if you really don't care to do it. But I honestly suggest you should practice this with an actual legitimate practice and trying to do this. Because like I said, they're easy points when you actually see these problems show up on the AP exam. And I want you to get those easy points. Okay? All right. With that being said, you can submit these notes once those are done. Notes are notes. They're in there. The homework, please get those done whenever you can. It's quite a few problems. 1 through 7 is going to be quick, though. But the rest of them, 1, 2, 3, 4, 5, 6, 7, 8 problems there is just asking you to evaluate some of these integrals or some of these areas right down there. So get those done for me. Submit that. I set around due date again, like I said, but yeah, 17. yeah. But the first 7 problems don't count, Monica. They're too easy. They're too easy. Look at this. Look how easy these are. Okay, okay, I'm gonna zoom out and just go away from that. They look difficult, but watch. Once you start doing them, you're gonna realize 1 through 7, easy as cake. They're not as hard as what we did in the notes. And even then, those aren't that difficult. Anyways, guys, that's it from me today. I'm gonna wrap it up here. I do have office hours today from 1 to 2 if you need to stop by for anything. Be ready for a quiz on Monday. And other than that, I think that's it. Have a good weekend, guys. I'll see y'all on Monday. Stay out of trouble. Stay out of jail. Don't get pregnant. I'll see you guys, all right? Have a good one. Bye, everybody. Bye, David. Bye, Monica. Bye, Leslie. Have a great day. You too, Ava. So long. Bye-bye.